going on. So let's do this problem. I've been attempting it. It's the daily problem, and I'm going to try to do the July problems daily. Um, this problem I'm having a little bit of trouble. I can't. I mean, you could backtrack on it. Um, I don't see anything wrong with doing that. Um, but it's too slow. It will give me TLE, time limit exceeded. So while it does work for low numbers, it won't pass. This just shows the time limit exceeded. It won't pass for large numbers. It just needs to go to 16 instead of 1. So I'm looking through here, thinking about how I can fix this. So this is going until you have all the elements. This is really doing a lot more though. So, um, and we can check. Wait, hold on a second. Did I delete it? So I can check here. So this is sometimes you have to learn how to solve a problem. So you can do this one with backtracking. Um, oh, oops, that's wrong. You can use one with backtracking. It's pretty obvious, but yeah, if you're like wondering, okay, what did I do wrong? I can't figure out what I did wrong. So let's just go into debugging, because debugging is really valuable if you're not understanding something here. Oops, let's just take this bit. Okay, it's harder here. Include bits, SCC, and I haven't actually. I think I know how to do this now, but so I'm kind of coming in already prepared. Go here, push this back. So let's print F, equals D. What is N? N is just, N is a constant. Uh, maybe the size of this. Okay. We need to pass in variable, and then we call, I guess, vector answer. Oh, what the heck? Vector int answer equals gray code. And I don't know why I did that. I don't need a vector. That's all I want to do. Okay, and build this. So it's oops. Um, I just remembered you need a. Oops, the heck? What am I doing? You need a cast it in. Okay, now it should work. Let's see here. Okay, so that worked. So now, oh, I already have it here. So I run maybe 10, not too crazy. And we can see how many iterations. So let's see how many, let's do something here. Count equals 0, and let's say every time we run in here and increment the count, oops, make this global, initialize count to be 0 here, and then let's see out count at the end. Okay, just to see how many iterations it's making, to see why it's taking so long. Um, ideas. Okay, so we can see here that it's making exactly how many iterations I expect, which is, because I know that 2 to the 10 is that number. So actually it's making exactly the number of calls to the function as we expect. And if we go to maybe 16, so I already have computed it, 16 should give like 65,536. Um, that's the number of iterations, which is fairly reasonable to solve. Okay, it takes a while because I'm printing at each level, but let's see here. Well, it's doing that. Okay, so let's think here. So if this is doing what I think it's doing, which is giving the correct number of calls to the function, the thing that's making it take so long is this. Because basically what these are doing is making a copy of vector, which is increasing the time complexity. So, and it's making a copy of the visit array. So that requires some time. So one thing we can do is we can add this into here, and actually, while it's still finishing that, we can attempt that here. The reason why I didn't make these reference though originally, I wanted to be, I guess what's called a deep copy. However, a deep copy, it takes all of n time to be able to make that operation, which is what it was doing. But the thing reason I didn't do is because I thought there's gonna be multiple paths, but that might not be the case here. What's the problem? Okay, I can't bind that, so I have to initialize these out here. Uh, okay. Okay, still running. Okay. Well, this gave the wrong answer. It didn't start with 0. Oh, yeah. Freeze. Okay, this is taking too much resources. Crap. I gotta stop it. I really hope the video doesn't freeze because of this. Because of this code I executed. Okay, stop it. There we go. Okay, this is putting out way too much here. Maybe, anyways. I mean, yeah, if we think about the time complexity of this normally, it's going to be here. Time complexity normally would be like, so it's iterating through n, but it also has the 2 to the n times n. So if you include the visited and the b, it has to create those. Then we have this squared, which might be too much. Okay, visit dot insert 0 b push track 0. We're just gonna start with 0 and run code. Sweet, it worked with 14, so I don't see why it's not gonna work with 16. And this is, yeah, so just test it out. Okay, so I think that's gonna fix what I had. So the code I had written at the beginning of the day, and then I had to work on some other things, was correct. This probably I had to come back to. But I just need to pass it as a reference. And I mean, I thought about this instantly because I know when I was doing this that, it's going to take more time complexity. I just thought for some reason that it's going to be, it needs to make a deep copy because it's going to be a bunch of different paths that it's taking, but it turns out it's only taking one path, and then it backtracks from that single path. So that changes the problem quite a bit. So that means like here, let's say if you have n equals to 2, so at the beginning, or let's do n equals 3. So at the beginning it'll do 0, 0, 0, then it'll do 0, 1, then it'll do, because what this code is doing, it's taking the ith one and setting that bit if it's not in count. So then, so when we go to the second iteration here, and it's doing this, it's going to start out, how do I write this? So it calls the function backtrack for the current number, which is 0, 3, and this is what we have currently. So it does that. Now, iterates through here, I equals 0, I less than n, this one, okay, so it's going to iterate through from basically it's going to set the bits, set a single bit from 2 to the 0th to the 2 to the n minus 1 bit. So I'm going to set the single bit from 2 to the 0 to 2 to the n minus 1 bit. So the first one he'll do is going to be this one. So then we're going to call backtrack. I think it's 1, 3, and then I'll just write these out in the bit format. So it's as these two. I'll just write it out once, but it's the same for both of them. So this is the vector it has so far. And then it does the same thing again. So the first thing it will do is it's going to set the first bit, but if it does that, if it toggles the first bit, it's just going to have 0, 0, and that should already be invisited. So then the next one it should do is 3, 3, 0, 0, 0, 0, 1, 0, 1, 1, like that. And then now I'm going to write that out in more simpler terms. So it should do this, 0, 1, 0, 1, 1, should generate this one, and it should generate this one. Actually, my bad, no. It should generate this one, and then it should generate this one, then should generate this one, and then it should generate this one, and then it will generate this one. Nope, that's not true. Yeah, so when it generates this one, then it's going to generate this one. Then it's going to try this, but this one we've already done, so it won't do that. It will do this. Then it will try this. Then it's going to try this, but we've already done that. So then it's going to try this. Then it's going to try this. Then it's going to try this. We've already done that. It's going to try this. We've already done that. So it's going to try this. Hold on. I'm writing this out wrong. Okay, I know it's doing each iteration now. So if n is equal to 3, first off I wrote out too many, so it's going to start with this one. It's going to go to the next. First thing is it always tries setting the very first bit. So it's going to try this one, and that was not in my visit rate, so I'll do that. Then it's going to take that current number and then do this. So the first thing is it's going to start over iteration at the beginning, so it's going to toggle the leftmost bit. So if I refer to this as bit number 321, so the first, second, and third bit. So the first bit will be toggled, but 00 is already in visited, so won't use that. So we'll keep this one, we'll go to the next one, so toggle that one. This one's good. Then we go to the next, a new iteration, a new call to the function, and it will try toggling this first bit, as always, which actually works. And then it's gonna try this again for the next iteration, a new iteration. That's already visited, so it's not gonna do that. Then it's gonna try toggling the middle, which would give this, which is already visited, so we're not gonna do that. So then it'll toggle the third bit, which is not, so that one works. The next one will try toggling the first bit again, a new clean iteration. That one actually works. The next one will try toggling the first bit, which won't work. I'll try toggling the middle bit, which will work. This one will try toggling the first bit, which does work. And then it stops. 1, 2, 3, 4, 5, 6, 7, 8. So you have 8. You only need 2 to the 3 terms, which is 8. So a backtrack. So if you have a backtrack algorithm like that, you're really just depending on the previous number. So I don't even think you need to write a recursion function for something like this. This is an interesting one for me, because here I wrote all this out. But the thing is that you're basically iterating through, you're checking, there are a total of 2 to 38 combinations that you must check. So let's try doing it without backtrack. I guess that'll be the challenge here. So this is pretty easy. I say I return true here, and I set A equal to B, but another way would probably be just to return B. Don't need A. And just say when B is equal to this size. No reason to continue. Yeah. Okay. So now let's save, do it using a stack space, no stack. Okay, so I'm gonna visit it. We'll have we'll almost initialize everything. And then, I'm not gonna do this. So for 0, I less than, so we know there's gonna be potentially this many states. So this here, 1 shifted to the left in times is basically 2 times n minus 1, or 2 times n. So this is equal to 2 to the n. I less than n, I plus, and then it's has to be a different variable, j, maybe, and j. Okay, and then this one we'll do, yeah, this is a good example of backtrack problem. Good problem. I need to practice these more. So hopefully I get some more backtracking in the future here. Let's see. Okay, so then these are all my states. This is all this. So I'd say generate my number again by taking the previous number, which will be the last number in this one. Toggle one of its bits. Specifically, we can iterate through, because we're iterating through n bits that we could toggle. So let's use this iteration through n's here and do this j. So we toggle the jth bit, toggle the jth bit and the previous number, and then basically say, oh, did I miss this thing? And then basically say, hey, if visited dot count of num equals to 0. So that means I haven't visited, then like, I guess from the example I did down here, I want to push back this num and break. Like I want to go to a clean iteration. Basically, I don't know, is this really a backtracking problem? Like, you're not really backtracking ever. You don't have to. You just go to a clean iteration and keep track of your previously seen. So yeah, it goes to a clean iteration. This is the total number of iterations we're gonna have because we need to generate a sequence of this length, and each element will differ by exactly 1 bit. So yeah, so we're guaranteeing generating a sequence of 2 to the n numbers, and here we are toggling a single bit be different than previous number and resulting gray sequence. And then here we are toggling the jth bit and check if it has been used before. And then we return B. That should run faster. That's interesting. Okay, did a bunch of repeats. I never like added these, did I? Into here. Okay, so that should work. Looks at related topics. Yeah, it says backtracking, bit manipulation for sure, backtracking. Sure, similar questions, 1-bit and 2-bit characters. Okay, maybe I'll try. That might be a good problem to try. Why is it so slow? Huh. Yeah, my code is slow, so maybe I can. I guess the next challenge would be, can you use a bitmask for this? Instead of maybe an unordered set of integers of numbers, which I don't think so. Let's get maybe discussion real quick. Because if mine's that slow, then I'm just a little curious. Okay, he called it backtracking. bit set. Yeah, so that means I'm not doing something optimal in C++. You create a bit set of 32 bits. Hmm. Yeah, this is what's hard. It's hard to come up with a proof that would work. I didn't know this would work though. It takes the ith value. So you start with 0, and you go to 1. Hmm. Yeah, but this one's hard. This is a hard proof to come up with. It's harder to see this than just doing pure, um, because this is not using the previous value of the answer array. Yeah, this is the math part. It's a math formula relationship for generating these gray sequence, the gray code. That might just be, yes, this is the problem. What if I have no, yeah, knowing the formula, it can be solved, which makes it kind of horrible. So I kind of did it without the formula. Yeah, so he did the same thing I kind of found. There's a lot of approaches. Hanoi, I actually haven't solved the Hanoi problem. No, that's a classic problem. I'll have to do that sometime. C++, let's just say C++ because I still want to see what's unoptimized. Oh, you know why my code is slower? Because I'm not using the math formula, and then when you use the math formula, you can do it 2 to the n. I mean, okay, yeah, that'll probably speed it up a lot. But wait, I still wanted to see, I always want to pick up new tricks for C++. This one takes 0 milliseconds. Yeah, so this is 2 to the n, not n times 2 to the n, so obviously mine's not going to be that fast. That one's weird. Okay, I see. So the only way to be able to make it faster is to get rid of this part and to use the math formula. I mean, I'm glad you can solve it without the math formula, but to be able to do better than this, you have to use the math formula. But that's not really like probably a good problem because if you just know that, like, you're just gonna know the math formula, or you're just not gonna know the math formula. But being able to do it with this solution here, though, is more like just deriving this relationship that's more more general in the sense that it's backtracking algorithm with 2 to the n combinations. So you need to iterate through 2 to the n, and you need to always take the previous number and you start a clean iteration each time. So that's one way to do that. So if we do it this way, we won't need this, and we won't need this if we use the formula, and then this will have to be resized to, it should be sized to this, I guess start at 0, and then bi will equal I, like so. That's the formula, and then you return that. Okay. Oh. What? Is that not the formula? Oh, maybe this is the formula. This might be the formula. You might be actually dividing I by 2. Okay, let's just think about this. What this formula would be doing, now that I already kind of have an idea, I can derive it more easily. But yeah, this kind of sucks. Like, I gotta know that. 0, 0. So the first one is gonna be 0, 0, 0, right? According to this, because you're taking 0 to the power of 0 shifted multiplied by 1. Let's say divided by 1. Wait, wasn't that what I was doing before? What the heck? I'm confused now. Yeah, this is what I was doing before. Wait, what? Okay, so what does this mean here? 1 to the power. This means 1 shift left I times. So this is equivalent to 2 to the power I bith. And then the other one I tried was this one. This one's equivalent to, or try. This one's equivalent to, actually this is I divided by 2. Oh, well that's different. Okay, but basically in terms of bits, what it means is we are shifting the the bits to the right by 1, but there's no, so we get 0 for our first iteration. Second iteration, we're gonna take 1, and we're gonna toggle 1, and we're gonna shift its bits over by 1. So if we do that, we're basically taking 1 toggled with 0. So that's just gonna give 0, 0, 1. And then we do the same thing for the next one, and we do 2, let's see, 2 toggle, let me think here, 2 toggle with 2 over by 1. This is basically like doing this. So if you take 2, 2 is normally this, and you move the bit over by 1, you get this, which is just 1. So this is 2 to the 1, so this would be this. That's not correct. It should give me 3 next. What did I do wrong? Oh, sorry, yeah, it's 2 toggling the first bit, so that's actually 3. That's actually this. And then we go to the next one, where it's going to be 3, and we're going to move over this bit by 1. So this is basically 0, 1, 1 toggled with, and if we move over by 1, it's this. So it's going to generate this one. So it's generating like the same pattern actually as what I did above, I think. Looks like. But it's just a formula that you can derive. I mean, if you look at this, can I see it? There's this relationship. Let me think. So 0 is 0. So 1, if we take 1 and we XOR it with 1 shift over by 1 bits, you're going to get this. You do this, and you shift over by 1 bits, you're going to get 3. You do this, this is going to be number, wait, what number is this? 0, 1, wait, 0, 1, this is 2, and then this is 3. So at 3, you're going to take the number 3 and XOR it with 1, which will give you this. And then you're going to take the number 4 and XOR it with 2, which will give you this. And here you're going to take the number 5, 5, and then XOR it with 2. Oh, wait a second. So at the beginning, you're taking the number, so you have 0, 1, 2, 3, 4, 5, 6, 7. So what it's doing is taking 0 XOR with this. It's taking 1 XOR with 0. Now we're taking 2 XOR with 0. Now we're taking, sorry, 2 XOR with 1, right? Because 2 divided by 1 is that. Then we're taking 3 XOR with this, 4 XOR with 2, 5 XOR with 2, 6 XOR with 3, 7 XOR with 3. So what's the pattern here is basically you're taking the current number and then your XORs with the current number divided by 2. That's what you're doing. And that generates this math formula. Formula generates a gray code sequence. Um, it it generates one gray code sequence. It generates one gray code because give me multiple. It generates one gray code sequence um, for a simple enough problem. So it kind of makes sense, you know. It kind of makes sense that if you do this, take the current number XOR with the current number divided by 2, you're going to generate all the gray code. Actually, that's kind of hard to understand, but I guess using the basic backtracking, I can kind of work out this formula, kind of observe this pattern and then test it. But yeah, it would be really hard to understand the math formula. So I think mostly this problem is solvable by just doing backtracking and ideas and concepts. Even though when I did that, you know, my solution was n times 2 to the n. But then, of course, I guess once you observe the pattern here and you see this kind of looks like an equation, maybe then you could get it down to 2 to the n time complexity, which then will allow you to improve, maybe hopefully get 0 milliseconds. 8 milliseconds is good enough. Yes. Nice. Okay. The other thing that I realized for this problem, kind of this is the realization I had when I first did the problem, was this problem can also be probably solved with a graph. Um, with a graph, maybe this is a hypercube, I don't know, but this problem can also be solved with a graph because if you think about it, um, just you know, each number when you set 1 bit, those are kind of like so like 0, 0 may have these edges. This this might be a directed graph or whatever. So this is a directed graph, yeah. So what I'm saying here is that for when you have n equals 3 and you have you start with the 0th number, that's the root of your graph or something maybe. the edges will be the 1, 2, and 4 because only the difference is 1 bit. So basically, you just set 1 bit and you add that as an edge, and you can build out a graph. And the interesting thing is that when you kind of get around to, and you can iterate through that graph. So I mean, you can generate this graph in 2 to the n time, I think. And then you can, and then there should be a cycle because once you get to like, let's say this number, right? Let's say, okay, this is the last number I get to. Like, okay, let's say we get to this number, right? The edges for this one are going to be this. Another edge would be this. Another edge would be this, right? But the problem with two of these edges will say, hey, we've already seen these. We can't traverse something we've already seen. So then we traverse this one. But the thing is that the edges for this one are going to be this. Well, they're going to be this. They're going to be, and another edge will be this. And another edge will be this. And you can see this is a cycle. So there's a cycle. So what you want to do is find a path starting from 0 that will then go through all the nodes and then come back to 0. So you're looking for a cycle in the graph. Don't know if I have time for this. So viewing it in terms of a graph is maybe also worth exploring for a little bit because I've been thinking about it since I did the problem earlier today in the morning. So probably, I mean that's the thing. I had time to think about this all day because I looked at it like what time did I look? Actually, wait, I looked at it last night because I was up a little late, couldn't sleep. So I looked at it when it was loaded last night. So then, yeah, I mean, I like graphs, so why not do the graph? Okay, unfortunately for the graph, we need to keep it on this. I think there's a way to be able to do a bit set. I don't know. Visited, I need to keep track of visited this time. Um, I just realized constructing the graph is going to take 2 to the n, I think n times 2 to the n. And that's also how much space it's going to take. So obviously this problem is not as optimal as using like formula, but it's still worth exploring. So we're going to have an unordered map from int to maybe an unordered to maybe a vector int. Call this my graph. Say for int I equal 0, I less than, we want to iterate through all of these, and then graph of this thing. Oh, then we have to iterate through for int j equals 0, j less than n, j plus plus, and then int num will equal I XORed this shift over by j toggle this bit, toggle the 2 to the jth bit, toggled. So we take our graph at I at this edge vertex, this vertex, and then we want to insert on, not insert because I'm using vector, push, oops, push back this num. So this is an edge. So the directed graph. So this should generate the entire graph. So we can look through it too. We can say we can do this here, something like this, and say for int x in graph I print f I equals d x equals d I x and get rid of that and then get rid of this. Run that. So yeah, so 0 has 1, 2, maybe let's use 3. 3 has more. Yeah, so 0 has 3, 1 has 3, 2 has 3, 3 has 3, 4, and so on, so on, so on. So basically they all have n is 3. Okay, so then see, yeah, so then if we look at this actually, if we look at this graph, we can see we start at 1, then we can traverse to 1. So which one of these traverse back to 0? So 4, 2 traverses back to 0, and 1 traverses back to 0. So those are the 3 numbers. There's 3 numbers that should traverse back to 0. And it might be multiple like possible cycles. That's where it comes in that there's multiple gray code sequences. Let's see. So to iterate, we just want to iterate through this graph. So we just want to say so B, guess we'll start like this, and we'll do B dot pushback 0. So that'll be the first element, and then 4. Okay, we know we're gonna have to do this many iterations. So then we will say int num will be the last element here, or hold on, 4, and I need to make sure that I know that this one has been seen, and I say 4 int neighbor or edge. Well, this is the neighboring node in graph, and we use our last number. So for this thing, if visited dot count of the neighbor is equal to 0, so we haven't visited or anything, let's actually insert that neighbor, and then let's add it to the array, and then let's break, and that should work. Now the interesting thing about when you look at it from this perspective is, what you may notice is that basically what I just did here is basically the same thing, and it's also the same, well, it's actually even slower because of the pre-processing here and then iterating through it again. So basically doing 2 to the n, doing it like an n times 2 to the n, and then a 2 to the n, like a 2 pass through 2 to the n, which is even worse. But this is very similar to this solution. So this solution is actually kind of like a graph. It can be thought of as a graph problem. And this is just kind of like just pre-processing graph, like building the graph more how you used to, building an adjacency list or whatever, attaching the edges when I represent a graph with an unordered map. And then basically just iterating through and finding the neighbors for each graph. Here, you're doing the same thing. You're finding the neighbors for this element because you can have up to n neighbors. You're just generating the neighbors on the fly, and then you're doing the same thing. So it's actually the same thing. I just wanted to show how this is a graph problem. And then probably if we really want to like maybe mix this up, we could even generate a different sequence. So see how I'm generating this sequence? Let's say, um, yeah, so see how I'm generating that sequence? What if, I'm just exploring this problem, so you're just watching me explore this now. What if we iterate this in a different direction? See what happens. Yeah, nice. So now we get a different gray sequence code, and we can see how there's multiple gray sequence codes based off of how we're like attaching our edges in our graph. There's multiple cycles to be able to go from 0 all the way back to 0. So here you can go to 4, 6, 2, 3, 7, 5, and then 1 also goes back to 0. This one, 4 goes back to 0, which is true. There's probably another one where 2, because 2 also can map to 0, right? There's in case they map to 0. To be able to get 2, probably, um, this is kind of stretching it. I can like hard code it into this problem to be able to probably cycle back from 2. If I do, I'm just hard coding for this problem. This is an exercise, really. I'm just practicing graph problems while I'm doing this. Figure it's good to record this. Alright, let's see what this gives me. So now I'm just hard coding different possible like setups of the graph. Okay, so that gives me the 4 still. Um, there's another way to do this. So I could start from 2 and then go to 1 here. Nice. So we did it. See, now we have 2 here. So we've been able to have 4 at the end, 1 at the end, or 2 at the end. So we see that there are 3 possible gray code sequences at least for when n equals 3. And I would imagine that it's basically there's at least n. There might be more because like I haven't really looked at these combinations in here, so this might be more of a let's see, more of some more complicated. I didn't really pay attention. I just paid attention to the last number. So just in terms of the last number cycling around. Yeah. Anyways, I don't know why I did that, but I just want to show how this is really a graph problem. And I think you can go even further because if it's a graph problem, let's see, gray code sequence. Let's take a look here at the other representations. Okay, let's just search. I didn't mean to click that. Search this. Paths on a hypercube graph. Hamiltonian cycles. Uh, oh, discrete maths. graph theoretic. Yeah, so I've never gone this deep actually. Actually, I might look at this just for the fun after this. Let's just look at this real quick, because I am not too much on the terminology. And I think a hypercube is just a n-dimensional cube. Yeah, n-dimensional analog of a cube or a square. It's kind of difficult. So probably, I guess a cool exercise would be maybe generating these graphs, visualizing them for the gray code sequences. Hamiltonian path is a path in an undirected or direct. I think in my case, yeah, I have a directed graph that visits each vertex exactly once. Ah, yeah, well, I didn't know that was the name of it, but yeah, that's what's going on here. You're visiting each vertex at least once in the graph. So this is a Hamiltonian path. A Hamiltonian cycle, a Hamiltonian path as a cycle, and this is a cycle because it goes really back. So path and cycle existing graph is the Hamiltonian path one, which is NP complete. Would be interesting to take a look more into that. You can see these kind of graphs. I could draw, if I had my freaking thing, I could draw what the graph looks like. Because this kind of represents the graph that I have, right? Because I'm going to have a pointer here, but it's going to be an n-dimensional cube. So actually, I think, oh, what the heck? Yeah, that's what I was looking at something earlier. I think when you do this one, if n is equal to 3, I'm guessing it's going to be a 3-dimensional cube. And if 4 is going to be a 4-dimensional cube. So on, so on. Yeah, because what's going to happen is, because in the case of n equals 3, it's kind of like this, right? You have the vertex here, and this vertex connects, it has 3 edges, right? 1, 2, 3. So when you have 3 edges, you're going to create like a 3-dimensional object. Here, if you have 4 edges, I think this one has 4 edges. One, okay, well, I guess it's kind of hard to see, but yeah, 1, 2, or this one here. So this one has 4 edges. It's connected here, 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 and to here, I believe. So this is a 4-dimensional representation. Um, so to explore this further, maybe might want to look at some tutorials on this. Oh, find a problem. Backtracking Hamiltonian cycle. Print all Hamiltonian path present in a graph. This one may like actually show you some practice problems. So it has a practice problem. This is checking whether or not it has a Hamiltonian path. Another one would be just see if there's anything specific to delete codes. Find if there's crap. There's a lot of problems that can be solved with Hamiltonian path. Ooh, okay. Yeah, so it might be interesting to explore. You can just try to in a weight diagram. So this problem, I wouldn't read it, but I would just kind of approach this problem, find the shortest superstring, and maybe see how, because if you understand Hamiltonian path, if you want to understand how they work in the graph, it's probably what I'm gonna do. So I'm gonna actually, I don't know why I thumbs it up. I didn't try it. But a review. Um, yeah, I would explore this problem because if I want to learn Hamiltonian paths, develop a deeper understanding, want to see how I can apply it to some random problem, that's always good exercise. Looks like unique path, cracking the safe, a couple other problems. Find the shortest superstrings going 2 times. So looks like about 3 problems on leak code, maybe more. Probably could find some problems elsewhere as well. So those are good problems with Hamiltonian paths to continue learning. And the other one would be what else was related to gray code? Um, can I actually, can I see the graph? I want to see a picture without, I'm not going to generate my own picture, but here, here's a nice picture. Hamiltonian cycle. And then I think this is a good picture of the case that I did with 3. So you can see 3 edges for each one. You can view it as directed. You can see it here as well. Um, this is 4. So this is harder to understand, but this is going to be 4-dimensional. And then it connects down there. Okay. I want to look at this one. Yeah, it's 4-dimensional as well. You can kind of see it's getting kind of complicated. Wouldn't really want to graph anything more than that. So another fun exercise might be, you can maybe try, but yeah, I mean, looking at these pictures kind of help gives the visualization aid to the gray code sequence and some of the deeper properties that can lie within it, such as the graph theory that relates to it, the Hamiltonian cycle that relates to it, a Hamiltonian path, which is a cycle because there's a cycle in the gray code sequence. And this is basically what you're doing when you're doing the first implementation of my code. I'm basically iterating through this n-dimensional hypercube graph. But of course, the second solution using math formula, I'm not sure how that relates to the graph. Maybe it does somehow. But the other thing would be visualize graphs. Yeah, so let's see this visualize graphs. Okay, well, I'm just looking around. I'm still looking for a good tool for visualizing graphs. Alright, that's it. So I'm going to try to do these for every day for July's leak code problems.